Stubs and skeletons in Java remote method invocation. Now we are focusing on stubs and skeletons. Uh, a stub for a remote object act as a client's local representative or proxy for a remote object. The caller invokes a method on the local stub which is responsible for carrying out the method call on the remote object. In RMI, the stub for a remote object implements the same set of remote interfaces that a remote object implements. Here you can see RMI stub passing mechanisms. We have already seen that RMI client can obtain a stub to a RMI server via registry. But consider the fact that the stub is already stub. But consider the fact that the stub is really just an object that is instantiated on the same machine as RMI server. That the registry serializes and send to the RMI client. Note, technically the registry does not have to be co-located on the same machine as RMI server object. Therefore, the stub may initially get serialized and sent to the registry machine before client requests it. And stubs can be passed in two other ways. Stub passed as an input parameter to another stubs method, and stub is stub returned by another stub method. So this has several implications. RMI stub can serve as factories for more stubs by returning stubs. Not all stubs need to be bound in the registry to be used, and some parts of the system may not need to bind a stub into registry at all. They send their stubs to other parts of the system via input parameter of methods of their stubs. At least one stub somewhere needs to be bound in the registry. That's the stub that starts everything else. A number of stubs bound in a registry should be kept to an absolute minimum, that is only one. More than one RMI client may use the same stub. Technically, different copies of the same stub from the RMI server machine. Stubs can be replicated by passing them around the network, creating multiple RMI clients all connected to the same RMI server. But we can see from these conclusions that if we bind a very few factory objects as stubs into the registry, that is only one from these factories, we can dynamically bind our networked system. But there's a drawback. Each stub consumes system resources in the form of allocated ports. Once a stub is tied to a port, the ability of other entities use that port is severely limited, if not completely excluded. This can severely impact the system and cause other headaches, such as having to reduce the system safely by opening more ports through the firewall. Here you can see RMI client machine, registry server, RMI server machine. Here you can see RMI stub is bind to the registry, and RMI stub lookup from registry from this RMI stub to the RMI client machine. And here you can see RMI server objects is here. RMI stub passed as input parameter to stub method. RMI stub here, and here you can see RMI server object here. RMI stub return from stub method here. Here you can see a proxy pattern. The stub and skeleton layer of RMI lie just beneath the view of the Java developer. In this layer, RMI uses the proxy design pattern as described in the book Design Patterns by Gamma, Helm, Johnson and Lizards. In the proxy pattern, an object in one context is represented by another proxy in a separate context. The proxy knows how to forward method calls between the participating objects. This diagram illustrates the proxy pattern. The RMI use of the proxy pattern, the stub class plays the role of the proxy, and the remote service implementation class plays the role of real subject. And a skeleton is a helper class that is generated from RMI to use. Skeleton understand how to communicate with stub across the RMI link, and skeleton carries a conversation with the stub. It reads parameters for the method call from the link, makes a call to the remote service implementation object, accept a return value, and then writes the return value back to the stub. In the Java 2 SDK implementation of RMI, the new wire protocol has made skeleton classes obsolete. RMI uses reflection to make connection to the remote service object. You only have to worry about skeleton classes and objects in JDK 1.1 and JDK 1.1 compatible system implementation. In this diagram, we are considering about the proxy pattern with related to stubs. Here you can see the subject interface and the request method and in proxy is connected to real subject, and real subject is passed from proxy to real subject. Here you can see some stubs and skeletons. Remote clients communicate with server object via stubs and skeletons. These stubs and skeletons are automatically produced by the Java compiler on class files that extend unicast remote object and have an interface that extend remote. These stubs and skeletons are implementation of proxy design pattern, which is related to decorator design pattern. Stubs and skeletons are adapters that first adapt the client to the internet and then the internet to the server object. Any serializable object that is implement serializable can be transmitted to the server by use of an input parameter if a method of the iRemote object interface. Any serializable object can be sent to the client by use of a return value of a method of iRemote interface. Any method of a serializable non-unicast remote object set to the client run on the client. A class server must be running in order for the RMI registry to initially load the stubs in preparation for transmitting them to clients. Here you can see a client with the iRemote object. The remote object appears local to the client here, and here you can see iRemote object. The client deals with an interface, not the remote object directly. Here you can see remote indicates that the object is remote, and here you can see remote object stub, remote object skeleton. On the client side, the stub is transmitted to the client when the client asks the server's RMI registry for the client for the object bound to a specific name. And here you can see remote object skeleton, object, remote object. On the server side, the stub communicate with the skeleton, not with the remote object directly. You can see the remote object here, the object that the server wishes to remote clients to use. And here you can see unicast remote object contains the code necessary to create stubs and skeletons. Now we are considering how code base is used in Java RMI. Here you can see downloading Java RMI stubs. Using Java RMI, applications can create remote objects that accept method calls from clients in other VMs. In order for a client to call methods on a remote object, the client must have a way to communicate with the remote object. Rather than having to program the client to speak the remote objects protocol, Java RMI uses special classes called stubs that can be downloaded to the client. that are used to communicate with make method calls on the remote object. The java.rmi.server.codebase property value represent one or more URL locations from which these stubs and any classes needed by stubs can be downloaded. Like applets, the classes needed to execute remote method calls can be downloaded from file :// URLs, but like applets, a file : // URL generally requires the client and servers reside on the same physical host unless the file system referred to by the URLs made available using some other protocol such as NFS. Generally, the classes needed to execute remote method calls should be made accessible from a network resource such as HTTP or FTP server. Remote objects code base is specified by the remote object server by setting the java.rmi.server.codebase property. The Java RMI server registers a remote object bound to the name, and with the Java RMI registry, codebase set on the server VM is annotated to the remote object reference in the Java RMI registry. Java RMI client requests a reference to a named remote object. The remote object stub instance is what the client will use to make remote methods calls to the remote object. 3. The Java RMI registry returns a reference, the stub instance, to the requested class. If the class definition for the stub instance can be found locally in the client's class path, which is always searched before the code base, the client will load the class locally. However, if the definition for the stub is not found in the client's class path, the client will attempt to retrieve the class definition from the remote object's codebase. 4. The client requests the class definition from the codebase. The codebase client uses is the URL that was annotated to the stub instance when the stub class was loaded by the registry. Back in step 1, the annotated stub for the exported object was then registered with the Java RMI registry bound to the name. 5. The class definition for the stub or any other classes that needs is downloaded to the client. Note step 5, 4 and 5 are the same steps that the registry took to load the remote object class. When the remote object was bound to a name in registered the Java RMI registry, when the registry attempted to load the remote object stub class, it requested the class definition from the code base associated with that remote object. 6. Now the client has all the information that it needs to invoke the remote method on the remote object. The stub instance acts as a proxy to the remote object that exists on the server. So unlike the applet which uses the code base to execute the code in its local VM, the remote RMI client uses the remote object's code base to execute code in another potentially remote VM, as illustrated in this figure. Using code base in Java RMI for more than just stub downloading here. In addition to downloading stub and associated classes to client, the java.rmi.server.codebase property can be used to specify location in which any class, not only the stubs, can be downloaded. When the client makes method call to a remote object, the method that it calls could be written to accept no arguments or a number of arguments. There are 3 distinct classes that may occur based on the Java data types of the method arguments. The first case, all of the method parameters and return values are primitive data types. So The remote object knows how to interpret them as method parameters, and there is no need to check class path or any code base. The second case is that the remote method parameter or return value is an object for which the remote object can find the class definition locally its class path. In the third case, shown in step 6, in this figure, the remote method receives an object instance for which the remote object cannot find the class definition locally in its class path. This type of remote method call is illustrated in figure 4, this figure. The class of the object sent by the client will be a subtype of declared parameter type. The subtype is either an implementation of the interface that is declared as the method parameter or return type, a class of the class that is declared as the method parameter or return type. You can see here Java RMI client making a remote method call passing an unknown subtype as the method parameter. And here is step 7, like the applet code base, the client specified code base is used to download remote classes, non-remote classes and interfaces to other VMs. If the code base property is set on the client's application, then the code base is annotated to the subtype instance when the subtype class is loaded by the client. If the code base is not set on the client, the remote object will mistakenly use its code base. Here you can see a server that exported a remote object. Here server registers a remote object bound to a name. Here step 1 is connecting a server that exported remote object, and here the java.rmi.server.codebase equal this address, and it's connected to server that registers a remote object bound to a name. And here step 2, RMI client is connected to RMI registry via client makes a naming.lookup call. Here step 3, RMI registry is connected to RMI client via the registry returns an instance of the remote object stub. Here RMI client is connected to URL location and my host here via client requests the stub class from the code base. Here my host or URL location here is connected to RMI client via HTTP server returns remote objects stub class. Here my host here URL location interacts with RMI registry. Here step 6, RMI client is connected to remote object instance via makes a remote method call. Here you can see RMI registry, and here server that exported the remote object. Here is step 6, here RMI client is connected to remote object instance. Clients make a remote method call passing a subtype unknown to the remote object as a remote method parameter. And here RMI client interacts with URL location. Here you can see the code base, and via code base property. Here remote object instance interacts with URL location via remote object downloads the subtypes class definition from the client specified code base. And consider this code segment. This stub object automatically created from this remote objects class file. This RMI stub object is instantiated by the same application that holds the RMI server object. The RMI stub object is transmitted to the client whenever a reference to the remotely accessible object RMI server object is established. This is actually this is the actual object that the client interacts with. The stub object simply delegates all methods across the network to its corresponding skeleton objects on the server. Here you can see the stub method is called. When a stub method is invoked, it does the following: initiate the connection with the remote JVM containing the remote object, marshals, writes and transmit the parameters to the remote JVM, wait for the result of the method invocation, unmarshals, read the return value or exception return and returns the value to the caller. Stub hides the serialization of parameters and network level communication in order to present the simple invocation mechanism to the caller. For the here you can see register the remote object with Java RMI registry. A caller, client, peer or applet to be able to invoke a method on the remote object, the caller must first obtain a stub for the remote object. For bootstrapping, Java RMI provide a registry API API for applications to bind a name to a remote object stub, and for clients to look up the remote objects by name in order to obtain their stubs. In Java RMI registry, a Java RMI registry is a simplified name service that allows clients to get a reference to a stub to a remote object. In general, a registry is used, if at all, only to locate the first remote object a client needs to use. Then typically the first object would in turn provide application specific support for by finding other objects. For example, the reference can be obtained as a parameter or parameter 2 or a return value from another remote method call. Once a remote object is registered on the server, caller can look up the object by name, obtain the remote object reference, and then invoke the remote methods on the objects. In this code, the server obtains a stub for a registry on the local host and default registry port, and then uses registry stub to bind the name hello to the remote object stub in the registry. The static method local registry.get registry that takes no arguments and returns a stub that implements the remote interface java.rmi.registry.registry and send invocations to the registry on the server's local host on default registry port of 1099. The bind methods is then invoked on the registry stub in order to bind the remote object stub to the name hello in the registry. Note, the call to locate registry dot getRegistry simply returns an appropriate stub for a registry. The call does not check to see if a registry is actually running. If no registry is running on TCP port 1099 of the local host, when the bind method is invoked, the server will fail with a remote exception. As an example, we can consider this java.rmi property, java.rmi server.codebase. This property specifies the locations from which classes that are published by this VM. For example, stub classes, custom classes that implement the declared return type of a remote method call, or interfaces used by a proxy or stub class may be downloaded. The value of this property is a string in URL format or a space separated list of URLs that will be the code base annotation for all classes loaded from the class path of and subsequently marshaled by this VM. Note, this property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will likely encounter exceptions when attempting to run your server or client. As an exception example, we can consider this one, stub not found exception, class stub not found exception. A stub not found exception is thrown if a valid stub class could not be found for a remote object when it is exported. A stub not found exception may also be thrown when an activatable object is registered via the java.rmi.activation.activatable.register method. This exception is in package java.rmi. As an error example, we can consider this error. It is occurred when creating. It was occurring when creating EDQ data server in DIPCC Governance Edition ODI Studio client. Failed to retrieve RMI server stub. javax.naming.service unavailable exception. Root exception is java.rmi.connection exception. Connection refused to host. Localhost. Nested exception is java.net.connection exception. Connection timeout at javax.management.remote.rmi.rmiconnector.connect rmiconnector.java, etc. Now we are considering stubs and skeleton related to client program. A skeleton for a remote object is a JRMP protocol server-side entity that has a method that dispatches calls to the actual remote object implementation. Here you can see how RMI architecture compares to the Open System Integration OSI architecture. The RMI application layer, like OSI application layer, contains the application programs. The stub and skeleton layer is similar to the OSI presentation layer in that it manages the remote object interface between client and server. The skeleton communicates with the stub except in Java 2.0 or higher, which has no skeleton. Once it obtain a reference to the remote object, the client can invoke it and receive the arguments of the operations allowed. The stub marshals and unmarshals the argument sent over the connection. OSI session layer is similar to the RMI layer that obtains a reference to the remote object from the naming registry service module. Finally, TCP, the TCP/IP network protocol packets encapsulates the transport layer. Transport layer contains Java Remote Method Protocol JRMP, also called the wire protocol. This shows RMI's architecture maps easily to the layers of more common open system integration OSI model. RMI architecture is highly suited for application servers that accepts code, data, and method calls from clients on fly. Persistent references let RMI control the number of active objects. The server can deactivate some objects so that the other objects can do their work. A client could reactivate the object on demand. Applications with many servers resulting many object references would benefit from RMI. Examples include airline reservation systems and enterprise-wide document archiving systems. Here you can see a client application interact with the stub, and stub interact with remote reference layer. Remote reference layer interact with Java remote method protocol. Java remote method protocol interacts with remote reference layer and remote reference layer is there, and JDK versions prior to 2.1 used a skeleton stub at this point, and skeleton stub is connected to applications, server application and remote reference layer. Here you can see with OS layers. In application layer you can see a client application and server application. In presentation layer you can see stub and skeleton. In session layer you can see a remote reference layer. Transport network layer you can see Java remote method protocol. Here you can see another diagram of RMI architecture. RMI gives a way for Java program on one machine to interact with object residing on different JVMs. The important blocks of RMI architecture are stub classes, skeleton classes, and object serialization. RMI needs a layered architecture where each of the layers may be enhanced without affecting other layers. Layers may be defined as this: application layer, a server, and the client program. Skeleton and stub layer, intercept method invokes made by the client and redirect these calls to remote RMI service. Remote reference layer. Setups connection to remote address spaces. Understand and manages connection, how to manage, interpret references given from clients to the remote service objects. Transport layer. Based on the TCP/IP connections between operating system in the network, it gives a basic connectivity as well as some firewall penetration goals. RMI stub classes give a reference to a skeleton object located in a different address space on the different or same machine. This is typical example of proxy design pattern, which builds an object executing another JVM seems like a local object. In JDK 5.0 and later, RMI facility access dynamic proxy instead of generated stubs, which build RMI easier to use. Here you can see RM client object looks up the stub in RMI registry and OGNID server, and RMI registry returns a stub to client object. Then stub method call on remote server objects to on skeleton, and skeleton send result and exception to stub. And here you can see the client and server is connected through cloud or network. Client is connected to the client process. Inside the client process you can see a client object, stub, and remote reference manager. Client object is connected, interact with stub. Stub interact with remote reference manager. And here you can see the server process. It has RMI registry, remote object, skeleton, and remote reference manager. Remote reference manager in client process is connected through RMI transport layer to remote reference manager in server process. And remote reference manager interacts with skeleton interacts with remote objects. And here you can see load stubs to RMI registry, and server is connected to server process. Here the note steps 4 and 5 are logical explanation only. Neither the stubs nor skeletons use sockets directly. The actual calls are made through the remote reference manager. Remote reference manager handles the actual details of communicating with remote process. This extra layer manages network communication and conserve scarce resources like sockets. Here you can see program 1 stub is connected to the skeleton, program 2 stub is connected to skeleton in program 1. We can consider this code segment as an example. The interface skeleton is deprecated, and the skeleton interface is used solely by the RMI implementation. Every version 1.1 and version 1.1 compatible skeletons generated in 1.2 using RMIC-V compact. Skeleton class generated by the RMIC stub compiler implements this interface. A skeleton for a remote object is a server-side entity that dispatches call to the actual remote object implementation. This interface is in java.rmi server. In the Java 2 SDK standard edition version 1.2, an additional stub protocol was introduced that eliminate the need for skeletons in Java 2 platform only environments. Instead, generic code is used to carry out the duties performed by skeletons in Java 1.1. Stubs and skeletons are generated by RMIC compiler. As an example, we can consider exception. If a general exception occurs in method void dispatch remote call int long in skeleton in interface skeleton. As an exception example 2, we can consider skeleton not found exception. It's a deprecated one. A class skeleton not found exception, no replacement. Skeletons are no longer required for remote method calls in Java 2 platform version 1.2 or greater. This is in package java.rmi.server. As an example 2, we can consider this example with the RMIC. When this command completes the stub, and skeleton should be located in the directory with the rest of the .class files. RMIC, the RMIC compiler generates stub and skeleton class files, JRMP protocol, and stub and tie class files, IIOP protocol for remote objects. These classes files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements interface java.rmi.remote. The class names in the RMIC command must be for the classes that have been compiled successfully with the javac command and must be fully package qualified. By default, RMIC generates stub classes that use the 1.2 JRMP stub protocol version only, as if the version 1.2 option had been specified. Note that the -v compact option was the default in releases prior to 5.0. Use the -IIOP option to generate stub and tie classes for the IIOP protocol. As an error example, we can consider this one. This error occurred while running this command rmic my remote impl invalid URL string, invalid URL string remote hello at java.rmi.naming.past URL at java.rmi.naming.rebind at rmiservice.myremote.implementation.main caused by java.net.uri syntax exception illegal character in path at index 6 remote hello, etc. As an example 3, we can consider this one. In the In the remote JVM, each remote object may have a corresponding skeleton. In Java 2 platform only environments, skeletons are not required. The skeleton is responsible for dispatching the call to the actual remote object implementation. When a skeleton is received, an incoming method invocation, it does the following: unmarshals read the parameters for the remote method, invokes the method on the actual remote object implementation, and marshals writes and transmit the result, return value or exception to the caller. In Java 2 SDK standard edition version 1.2, an additional stub protocol was introduced that eliminates the need for skeletons in Java 2 platform only environment. Instead, generic code is used to carry out the duties performed by skeletons in JDK 1.1. Stubs and skeletons are generated by RMIC compiler. Here you can see the stubs here with Java 2 SDK, the server side. Here you can see we can take this as example for compile source files, where dest dir is the destination directory to put the class files. Note that if server needs to support client running on pre 5.0 VMs, then the stub class for the remote object implementation class needs to be pre-generated using the RMIC compiler, and that stub class need to be made available for clients to download. Now we are considering stubs and skeletons layer. The stubs skeleton layer is the interface between the application layer and the rest of the RMI system. This layer does not deal with specifies of any transport, but transmit data to the remote reference layer via the abstraction of Marshall streams. Marshall streams employ a mechanism called pickling, which enables Java objects to be transmitted between address spaces. Objects transmitted using the pickling system are passed by copy to the remote address space. Here you can see the relationship among remote object, stub, and skeleton classes. Defining remote RMI object involves specifying a remote interface for the object, but then providing class that implements this interface. The remote interface and the implementation class are then used by RMI to generate the client stub and server skeleton for your remote object. The communication between local objects and remote objects is handled using these client stubs and server skeletons. Relationship among stubs and skeleton and object that use them are shown in this figure. When a client gets a reference to a remote object, details on how this reference is obtained we discuss later, and then calls methods on this object reference. There needs to be a way for the method request to get transmitted back to the actual object on the remote server, and for the results of the method call to get transmitted back to the client. This is what generated this is what the generator stub and skeleton classes are for. They act as a communication link between client and your exported remote object, making it seem to the client that object actually exists within Java. Within its Java VM. The RMI compiler, RMIC, automatically generates this stub and skeleton classes for you based on the remote interface and implementation class you provide. RMIC generates stub and skeleton classes that implements remote interface and act as go between the client application and the actual server object. The client stub class, the compiler generates an implementation of each remote method that simply packages up, marshals the method arguments and transmit them to the server. For the server skeleton class, the RMI compiler generates another set of implementation of remote methods. Remote method call, unpackage them and make the corresponding method call on object implementation. Whenever the method call generates a return data or an exception, the results are packaged and transmitted back to the remote client. The client stub method, which is still executing at this point, unpackages the result and delivers them to the client as the result of its remote method call. So the first step of creating your remote object is define the remote interface for the types of objects you need to use in the distributed object context. This isn't much different from defining public interfaces in a non-distributed application with the following exceptions. First point, every object you want to distribute using RMI has to directly or indirectly extend an interface that extend java.rmi.remote interface. Every method in the remote interface has to declare that it throws java.rmi.remote exception or one of the parent classes of remote exception. Note that prior to Java 1.2, the RMI specification required that every method on a remote interface had to throw remote exception specifically. In Java 1.2, this has been loosened to allow any superclass of remote exception. Reason for this change is to make it easier to define generic interfaces that support both local and remote objects. RMI imposes the first requirement to allow it to differentiate quickly between objects that are enabled for remote distribution and those that are not. As we have already seen during a remote method invocation, the RMI runtime needs to be able to determine whether each argument to the remote method is a remote object or not. The remote interface, which is simply a tag interface that marks remote objects, make it easy to perform this check. The second requirement is needed to deal with errors that can happen during remote session. When a client makes a method call on a remote object, a number of errors can occur, preventing a remote method call from completing. These include client-side errors. An argument can't be marshaled. Errors during the transport of data between client and server. For example, network connection is dropped. And errors on the server side. For example, method throws a local exception that needs to be sent back to the remote caller. The remote exception class is used by RMI as a base exception class for any different types of problems that might occur during remote method call. Any method you declare on a remote interface is assumed to be remotely callable, so every method has to declare that it might throw a remote exception or one of its parent interfaces. Here you can see this is step 1, define remote interfaces. Step 2, define server implementations. Here and step 3, generate stubs and skeleton using RMIC. Here you can see stub and skeleton are connected to remote interface, and here you can see the inheritance lines. Here implementation of remote interface is connected to remote interface. Here you can see the inheritance line, and here implementation of remote interface is connected to stub and skeleton class. Here you can see generated by RMC line arrow. Here implementation of remote interface is connected to remote object implementations. Here you can see instances arrow. Here stub class is connected to stub object, and you can see here instances arrow. Here skeleton class is connected to skeleton object. Here you can see instances arrow. And here client object is client object interacts with stub object. Here skeleton object interacts with remote object implementation. Here you can see communication arrows in both way. Here also. Here the remote interface and implementation of interface, implementation of remote interface interfaces or classes written by you. Here the stub class and skeleton class are interfaces or classes generated from RMIC. Here client objects and remote object implementations are objects created by you, and here stub object and skeleton objects are objects created by RMI. Now we are considering stubs. Here stubs and skeletons. RMI uses a standard mechanism employed in RPC systems for communicating with remote objects, stubs and skeletons. A stub for a remote object acts as a client, local representative or proxy for the remote object. The caller invokes a method on the local stub, which is responsible for carrying out the method call on the remote object. In RMI, a stub for a remote object implements the same set of remote interfaces that the remote object implements. When a stub method is invoked, it does the following: initiate a connection with the remote JVM containing the remote object, marshals write transmits the parameters to the remote JVM, wait for the result of the method invocation, marshals reads the return value, unmarshals reads the return value or exception returns and returns the value to the caller. The stub hides in the serialization of the parameters and the network level communication in order to present the simple invocation mechanism for the caller. In the remote JVM, each remote object may have a corresponding skeleton. In Java 2 platform, only environment skeletons are not required. The skeleton is responsible for dispatching the call to the actual remote object implementation. When a skeleton receives an incoming method invocation, it does the following: unmarshals read the parameters for remote method, invokes the method on the actual remote object implementation, and marshals writes and transmits the result, return value or exception to the caller. In Java 2 SDK, standard edition version 1.2 and at additional stub protocol was introduced that eliminates the need for skeleton in Java 2 platform-only environment. Instead, generic code is used to carry out the duties performed by skeletons in JDK 1.1. Stubs and skeletons are generated by RMIC compiler. Now we are considering stub and skeleton compiler. The RMIC stub and skeleton compiler is used to compile the appropriate stubs and skeletons for specific remote object implementation. For the Windows RMIC here, the Java RMIC compiler, the RMIC compiler generates stubs and skeleton class files, JRMP protocol, and stub and tie class files, IIOP protocol for remote object. These classes files are generated from compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the interface java.rmi.remote. This class names in the RMIC command must be for classes that have been compiled successfully with the Java C command and must be fully package qualified. For example, running RMIC on the class file name hello impl as shown here, RMIC hello impl creates the hello impl underscore stub.class file in the hello subdirectory named for the classes package. In Unix, RMIC deprecation note support for static generation of Java remote method protocol JRMP stubs and skeletons has been deprecated. Oracle recommends that you use dynamically generated JRMP stubs instead, eliminating the need to use this tool for JRMP based applications. RMIC compiler generates stub and skeleton class files using the Java remote method protocol JRMP and stubs and class files IIOP protocol for remote objects. These class files are generated from the compiled Java programming language classes that are remote object implementation classes. The remote implementation class is a class that implements the interface java.rmi.remote. The class names and the RMIC command must be for classes that were compiled successfully with the Java C command and must be fully package qualified. For example, running the RMIC command on the class file hello impl in Unix here, as shown here, creates hello impl underscore stub dot class file in the hello subdirectory named for the classes package. Here RMIC hello impl. The skeleton for the remote object is a JRMP protocol server-side entity that has a method that dispatches call to the remote object implementation. Now we are considering the remote stub class in stub and skeleton interfaces. The stub objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of a remote object. The class remote stub deprecated. Statically generated stubs are deprecated. Since the stubs are generated dynamically, the remote stub class is a common superclass of statically generated client stubs and provide the framework to support wide range of remote reference semantics. Stubs objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of the remote object. The java.rmi.server remote stub class is a common superclass for stubs of remote objects. Stubs objects are surrogates that support exactly the same set of remote interfaces defined by the actual implementation of remote object. First constructor of remote stub creates a stub with a null remote reference. The second constructor creates the stub with the given remote reference ref. The setref method is deprecated and unsupported as of the Java 2 SDK standard edition version 1.2. here the class remote stub is in the package java.rmi.server, which is in the module java.rmi. Now we are considering remote call interface. The interface remote call is an abstraction used by the stubs and skeletons of the remote objects to carry out a call to a remote object. The interface remote call deprecated, no replacement. The remote call is an abstraction used solely by the RMI runtime in conjunction with the stubs and skeletons of the remote objects to carry out the call to a remote object. The remote call interface is deprecated because it's only used by the deprecated method in Java. .rmi.server.remote.ref. Note the remote call interface is deprecated as of the Java 2 SDK standard edition version 1.2, and the 1.2 stub protocol does not make use of the interface anymore. As of Java 2 SDK, the standard edition version 1.2 stubs are now use the new invoke method, which does not require remote call as a parameter. The method get output stream returns the output stream into which either stub marshals arguments or skeleton marshals results. The method release output stream releases the output stream in some transports. This will release the stream. The method get input stream returns the input stream from which the stub marshals results or skeleton marshal parameters. The method release input stream releases the input stream. This allows some transport to release the input side of the connection early. The method get result stream returns the output stream after writing out the header information relating to the success of the call. Obtaining a result stream should only succeed once per remote call. If success is true, then result to be marshaled is a normal return. Otherwise, the result is an exception. The stream corruption exception is thrown the stream corruption exception is thrown if the result stream has already been obtained for this remote call. The method execute call does whatever it takes to execute call. The method done allows cleanup after the remote call has completed. The skeleton interface and the skeleton for a remote object is a server-side entity that dispatches call to the actual remote object implementation. Interface skeleton deprecated, no replacement. Skeletons are no longer required for remote method calls in Java 2 platform version 1.2 and greater. The skeleton interface is used solely by RMI implementation. This is in the package java.rmi.server, which is in the module java.rmi. The interface skeleton is used solely by the implementation of skeletons generated by RMIC compiler. A skeleton for a remote object is a server-side entity that dispatches calls to the actual remote object implementation. Note the skeleton interface was deprecated as of Java 2 SDK. The standard edition version 1.2 every 1.1 and version 1.1 compatible skeletons generated in 1.2 using RMIC-V compact, the default. The skeleton class generated by the RMIC stub compiler implements this interface. Skeletons are no longer required for the remote method call dispatch as of Java 2 SDK standard edition version 1.2 compatible versions. To generate stubs that are compatible with 1.2 or later version, use command RMIC with option -v 1.2. The dispatch method unmarshals any argument from the input stream obtained from from the call object invokes the method indicated by the operator number opnum on the actual remote object implementation object, and unmarshals the returns value or throws an exception if one occurs during the invocation. The get operations method returns the array of arrow containing operation descriptors for the remote objects methods. Now we are considering the operation class. The class operation holds a description of a method in a Java programming language for remote object. The class operation deprecated, no replacement. The operation contains the description of a Java method. Operation objects were used in Java in JDK 1.1 version stubs and skeletons. The operation class is not needed for 1.2 style stubs, hence this class is deprecated. This is in the class package java.rmi.server, which is in the module java.rmi. Note the operation interface is deprecated as of Java 2 SDK standard edition version 1.2. The 1.2 stub protocol no longer uses the old remote ref .invoke method, which takes the operation as one of its argument. As of Java 2 SDK standard edition version 1.2, stubs now use the new invoke method, which does not require operation as a parameter. The operation object is typically constructed with the method signature. Method get operation returns contents of the operation descriptor, the value with which it was initialized. The method toString also returns the in-string representation of the operation descriptor, typically the method signature. Now we are considering remote method invocation RMI tools in JDK tools and utilities. The tool RMIC here generates stubs and skeletons for remote objects. Now we are considering examples in command line examples in dynamic code downloading using Java RMI using the java.rmi.server codebase property. If the location of your downloadable classes is on the HTTP server named web vector in the directory export under the web root, your codebase property setting might look like this. And if the location of your downloadable classes is on the HTTP server named webline in jar file name my stuff in the directory public under the web root, if your code base property settings might look like this. And now let's suppose the location of your downloadable classes has been split between two jar files, my stuff.jar and my other stuff.jar. In these jar files are located in the different servers named webfront and webview. Your code base property settings might look like this. Now we are considering properties that are useful to set on virtual machine JVMs that export remote objects. Java.rmi.properties, Java.rmi properties, Java.rmi.server.codebase. This property specifies the locations from which the classes that are published by this VM, for example, stub classes, custom classes that implement and declare return type of remote method call, or interfaces used by proxy or stub classes may be downloaded. The value of this property is a string in URL format or a space separated list of URLs that will be the code base annotation for all classes located from the class path of and subsequently marshaled by this VM. Note This property must be set correctly in order to dynamically download classes and interfaces using Java remote method invocation, Java RMI. If this property is not set correctly, you will likely to encounter exceptions when attempting to run your server or client. Now we are considering properties that are useful to set on VMs that make remote method calls. Again, the java.rmi.server.codebase. This property specifies the location from which the classes that are published by this VM, for example, custom classes that are implement an interface that is declared parameter type of a remote method call may be downloaded. The value of this property is this property is a space separated list of URLs that will be a code base annotation for classes downloaded from class path of and subsequently marshaled by this VM. Note, classes that exist in both server's code base and client's class path will be loaded from the client's class path rather than from the server code base as intended.